Definition and scope of business intelligence, BI. Definition. Business intelligence, BI, refers to a technology-driven process for collecting, integrating, analyzing, and presenting business data to support better decision-making. BI encompasses a wide range of tools, applications, and methodologies that enable organizations to transform raw data into meaningful and actionable insights. At its core, BI answers key business questions such as: what happened? Why did it happen? What is happening now? What might happen in the future? Scope of business intelligence. The scope of BI extends across various layers of business operations, including strategic, tactical, and operational levels. It integrates data from internal and external sources to provide comprehensive insight into business performance and market trends. 1. Data sources and integration. Collects data from various sources such as ERP systems, CRM platforms, social media, and IoT devices. Involves ETL, extract, transform, load, processes to clean, structure, and store data in data warehouses or data lakes. 2. Data analysis and mining. Includes descriptive, diagnostic, predictive, and prescriptive analytics. Employs statistical models, data mining techniques, and AI or ML algorithms to uncover patterns, trends, and anomalies. 3. Reporting and visualization. Generates reports, dashboards, and visual analytics to present key metrics, KPIs, and performance indicators. Supports data storytelling to enhance communication and decision-making. 4. Decision support systems, DSS. Facilitates real-time and historical data analysis for informed strategic planning. Enables what-if analysis, forecasting, and scenario planning. 5. Business performance management. Aligns business activities with strategic objectives. Monitors and evaluates performance using scorecards and BI dashboards. 6. Applications across domains. Marketing, customer segmentation, campaign performance. Finance, budgeting, financial forecasting, fraud detection. Operations, inventory management, supply chain optimization. Healthcare, patient data analysis, resource utilization. Retail, sales analytics, demand forecasting. Why BI matters. Enhances data-driven decision-making. Improves operational efficiency and competitive advantage. Supports agility and responsiveness in a dynamic market. BI versus data analytics versus data science. 1. Business intelligence, BI. Focus, past and present business performance. Purpose, helps organizations make informed decisions by visualizing historical and current data. Key features. Dashboards and reports. KPIs and performance tracking. Data integration from business systems. Primarily descriptive analytics. Tools, Power BI, Tableau, ClickView, SAP BI. Use case, a retail manager uses BI dashboards to track weekly sales trends. 2. Data analytics. Focus, exploring and interpreting data patterns. Purpose, involves applying statistical and computational methods to extract insights from data. Key features. Covers descriptive, diagnostic, predictive, and prescriptive analytics. Involves querying, analyzing, and interpreting data. Supports both operational and strategic decisions. Tools, Excel, SQL, Python, R, SAS. Use case, an analyst evaluates customer churn rates using logistic regression models. 3. Data science. Focus. Advanced data modeling and prediction. Purpose, uses machine learning, AI, and algorithms to build predictive or automated systems. Key features. Predictive and prescriptive modeling. Big data and unstructured data handling. Emphasis on hypothesis testing, model training, and automation. Tools, Python, R, TensorFlow, Hadoop, Jupyter Notebooks. Use case, a data scientist builds a recommendation engine for an e-commerce platform. Importance of business intelligence in modern organizations. In today's data-driven world, business intelligence, BI, plays a critical role in helping organizations remain competitive, agile, and efficient. By leveraging BI tools and techniques, companies can harness the full value of their data to support smarter, faster, and more strategic decision-making. 1. Data-driven decision-making. BI enables organizations to make evidence-based decisions rather than relying on intuition. It transforms raw data into meaningful insights through dashboards, visualizations, and reports, empowering decision-makers at all levels. 2. Improved operational efficiency. BI tools help identify inefficiencies in processes, reduce costs, and streamline operations. Real-time data monitoring ensures quick adjustments in operations to avoid disruptions and enhance productivity. 3. Competitive advantage. With BI, organizations can perform market analysis, monitor competitor performance, and identify emerging trends. This proactive insight gives companies a strategic edge in adapting to market changes and seizing new opportunities. 4. Enhanced customer insights. BI helps track customer behavior, preferences, and feedback, enabling personalized marketing strategies, improved customer service, and higher satisfaction. It supports customer segmentation and targeted campaigns. 5. Forecasting and planning. By analyzing historical data and identifying trends, BI supports accurate sales forecasting, demand planning, and financial budgeting. This helps organizations allocate resources more effectively. 6. Performance monitoring. Organizations use BI to define and monitor key performance indicators, KPIs, across departments. Dashboards provide visual representations of metrics, allowing real-time tracking and continuous performance improvement. 7. Better risk management. BI tools help identify potential risks by analyzing patterns and anomalies in data. Early detection of fraud, compliance issues, or market volatility allows timely mitigation strategies. 8. Cross-departmental collaboration. BI promotes a unified view of organizational data across departments, improving interdepartmental communication and alignment toward common goals. Business intelligence lifecycle and architecture. Business intelligence lifecycle. The business intelligence (BI) lifecycle is a structured approach to transforming raw data into meaningful insights for decision-making. Here are the key stages. 1. Data sourcing. Identification of data sources, internal and external. Data extraction from operational systems, databases, APIs, etc. Assessment of data quality and completeness. 2. Data integration. ETL, extract, transform, load, processes. Data cleansing and standardization. Data consolidation from multiple sources. Creation of data warehouses or data marts. 3. Data storage. Data warehouse implementation, relational or dimensional models. Data mart creation for specific business units. Implementation of data lakes for unstructured data. Cloud-based storage solutions. 4. Data analysis. OLAP, online analytical processing. Data mining techniques. Statistical analysis. Predictive modeling. Machine learning applications. 5. Information delivery. Dashboard creation. Report generation, scheduled or ad hoc. Data visualization. Alert mechanisms for key metrics. Mobile BI capabilities. 6. Decision-making. Interpretation of insights. Strategy formulation. Operational adjustments. Performance monitoring. 7. Feedback and optimization. User feedback collection. System performance evaluation. Continuous improvement of BI processes. Model refinement based on changing business needs. Business intelligence architecture. BI architecture provides the framework for implementing BI solutions. A typical BI architecture consists of multiple layers. 1. Data source layer. Operational databases, ERP, CRM, SCM systems. flat files and spreadsheets. Web and social media data. IoT devices and sensors. External data sources, market data, government data. 2. Data integration layer. ETL tools, Informatica, SSIS, Talent, etc. Data quality tools. Metadata management. Data virtualization tools. 3. Data storage layer. Data warehouse, central repository of integrated data. Enterprise data warehouse, EDW. Operational data store, ODS. Data marts, subject-specific subsets of data warehouse. Data lakes, for storing raw, unstructured data. Cloud storage solutions, AWS Redshift, Azure Synapse, Google BigQuery. 4. Analytical layer. OLAP servers, Microsoft Analysis Services, SAP BW. In-memory analytics engines. Data mining tools. Predictive analytics engines. AI and machine learning models. 5. Presentation layer. Dashboards and scorecards. Ad hoc query tools. Reporting tools, Power BI, Tableau, Click. Mobile BI applications. Embedded analytics and business applications. 6. Metadata management layer. Business metadata, definitions, rules, ownership. Technical metadata, ETL processes, data lineage. Operational metadata, refresh schedules, usage statistics. 7. Security and governance layer. Authentication and authorization. Data encryption. Audit trails. Compliance management. Data privacy controls. Modern BI architecture trends is cloud-based BI, self-service BI, real-time and augmented analytics. Concepts of data warehousing. A data warehouse, DW, is a centralized repository that stores integrated data from multiple sources, optimized for query and analysis rather than transaction processing. It is a foundational component of business intelligence, BI, enabling organizations to make informed decisions based on historical and current data. 1. Definition. A data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data that supports decision-making processes. It consolidates data from heterogeneous systems like ERP, CRM, and flat files into a single, consistent data model. 2. Core concepts. A. Subject-oriented. Data is organized around key subjects like customers, products, or sales, rather than day-to-day operations. B. Integrated. Data is collected from various sources and transformed into a consistent format, e.g., unified naming conventions, data types, and units. C. Time-variant. Data is stored with a historical perspective, allowing for trend analysis, forecasting, and reporting over time. D. Non-volatile. Once data is entered into the warehouse, it is not changed or deleted, only appended, ensuring stability for analysis. 3. Architecture components. Data sources, operational databases, flat files, external data feeds. ETL process, extract, transform, load tools prepare data for storage. Data staging area, temporary space where raw data is cleaned and transformed. Data warehouse database, central repository storing subject-oriented data. Data marts, subsets of the warehouse focused on specific business lines. OLAP tools, enable fast, multidimensional querying for analysis. BI tools, dashboards, reporting tools, data mining applications. 4. Types of data warehouses. Enterprise data warehouse, EDW centralized, enterprise-wide platform. Operational data store, ODS real-time, integrated data for routine operations. Data mart. Smaller, department-specific warehouse, e.g., sales or finance. 5. Benefits. Consistent data for reporting and analytics. Enhanced decision-making capabilities. Historical data tracking for trends. Improved data quality and governance. Scalability for growing data needs. Data modeling, star schema versus snowflake schema. Star schema. Definition: a star schema is the simplest type of data warehouse schema, consisting of one or more fact tables referencing any number of dimension tables. Structure: central fact table surrounded by dimension tables. Resembles a star shape, hence the name. Dimensions are not normalized, contain redundant data. Components: fact table. Contains quantitative data, metrics/measurements. Stores foreign keys to dimension tables. Typically large in size. Dimension tables. Contain descriptive attributes. Connected directly to the fact table. Typically smaller than fact tables. Advantages: simple to understand and design. Fast query performance, fewer joins. Optimized for read operations. Works well with OLAP tools. Disadvantages: data redundancy, denormalized structure. Potential for data inconsistency. Less flexible for changes. Snowflake schema. Definition: a snowflake schema is a variation of the star schema where dimension tables are normalized into multiple related tables. Structure: fact table connected to dimension tables. Dimension tables are normalized, split into multiple tables. Resembles a snowflake shape, hence the name. Components: fact table, same as in star schema. Dimension tables, normalized into hierarchies. Subdimension tables, additional tables that dimensions reference. Advantages: reduced data redundancy. Better data integrity. More flexible for changes. More efficient storage, less duplicate data. Disadvantages: more complex queries, more joins required. Potentially slower query performance. Harder to understand and maintain. When to use each. Use star schema when query performance is critical. Simplicity is preferred. Working with OLAP systems. Dimension tables are relatively small. Use snowflake schema when storage space is a major concern. Data integrity is critical. Dimensions are large and hierarchical. The system requires high flexibility. ETL processes: extract, transform, load. ETL stands for extract, transform, load, a key process in data integration, data warehousing, and business intelligence systems. It involves moving data from source systems into a central data warehouse or data repository, ensuring it's clean, consistent, and useful for analysis and decision-making. 1. Extract. This phase involves retrieving raw data from various source systems. These sources may include databases, SQL, NoSQL, ERP/CRM systems, flat files, CSV, JSON, XML, APIs or web services, cloud platforms, AWS, Azure, Google Cloud. The main goal is to gather all relevant data, often from heterogeneous and dispersed systems, without affecting the source system's performance. 2. Transform. In this stage, the extracted data is cleaned, enriched, and converted into a suitable format for analysis or storage. Transformations include data cleaning, removing duplicates, handling missing values, correcting errors. Data mapping. Matching source data fields to destination schema. Data aggregation, summarizing large volumes of data. Data normalization/denormalization. Business rules application, e.g., currency conversion, tax calculation. This phase ensures data is consistent, high quality, and aligned with business needs. 3. Load. The final stage involves loading the transformed data into a target system, typically data warehouses, e.g., Amazon Redshift, Snowflake. Data lakes, e.g., Azure Data Lake. Analytical databases. BI tools, e.g., Tableau, Power BI. There are two common loading strategies. Full load, entire dataset is loaded from scratch. Incremental load, only new or updated data is loaded. Data quality and governance, description. Data quality refers to the condition of a dataset based on factors such as accuracy, completeness, consistency, reliability, and timeliness. High-quality data ensures that business decisions, analytics, and operational processes are based on trusted and valid information. Data governance is the framework of policies, processes, roles, responsibilities, and technologies that ensure effective and efficient use of information. It defines how data is managed, accessed, and protected across the organization, ensuring accountability and compliance with regulatory and organizational standards. Together, data quality and governance enable organizations to maintain trustworthy data assets, comply with legal and regulatory requirements, empower data-driven decision-making, reduce risks associated with poor data, establish clear data ownership and stewardship. Data quality challenges: poor data entry, manual errors, inconsistent data formats, e.g. dates as mm/dd/yyyy versus ddmmyyyy. Lack of standardization, e.g., USA versus United States. Siloed data, different departments storing data differently. Data quality improvement techniques: heavy checkmark data profiling, analyzing data to detect anomalies. Heavy checkmark data cleansing, correcting errors, e.g., deduplication, standardization. Heavy checkmark validation rules, enforcing constraints, e.g., email format checks. Heavy checkmark master data management, MDM, maintaining a single source of truth. Benefits of data governance: white heavy checkmark improved decision-making, reliable data leads to better insights. White heavy checkmark regulatory compliance, avoid fines, e.g., GDPR violations. White heavy checkmark reduced risks, prevents data breaches and misuse. White heavy checkmark operational efficiency, eliminates redundant or conflicting data. Data governance frameworks: DMBOK, data management body of knowledge. COBIT, control objectives for information and related technologies. DCAM, data management capability assessment model. Relationship between data quality and governance. Data governance sets the rules and accountability. Data quality ensures the data meets those standards. Example workflow. Governance policy: customer emails must be unique and valid. Quality check: system flags duplicate/invalid emails. Correction: data stewards clean and standardize records. Monitoring: automated checks prevent future issues. Tools for data quality and governance. Data quality: Informatica data quality, Talent, Trifacta. Governance: Calibra, Alation, IBM Infosphere. Data quality ensures data is accurate, complete, and usable. Data governance provides the structure to maintain quality, security, and compliance. Together, they enable trusted data for analytics, reporting, and AI or ML. Overview of popular business intelligence (BI) tools, including Power BI, Tableau, ClickView, now known as ClickSense, and Looker. Key features and descriptions. Microsoft Power BI, a web-based business analytics tool suite that excels in data visualization, allowing users to identify trends in real time and integrate apps to deliver reports and dashboards. It's accessible from anywhere and offers seamless integration with other Microsoft products. Tableau, a BI tool specialized in data discovery and visualization, enabling users to analyze, visualize, and share data without requiring IT intervention. It supports multiple data sources and offers several standalone products, including Tableau Desktop and Tableau Server. ClickSense, ClickView, a complete data analytics platform and business intelligence tool that offers associative analytics, sophisticated AI, and high-performance cloud platform. Its notable feature is search and conversational analytics, enabling users to ask questions and discover insights using natural language. Looker, a BI tool that offers embedded analytics, SQL, and business intelligence capabilities. It's known for its LookML dashboards and blocks, providing users with customizable and shareable dashboards. Looker integrates well with Google Analytics and other data sources. Other notable BI tools. SAP Business Objects offers comprehensive reporting, analysis, and interactive data visualization with self-service, role-based dashboards. Google Data Studio, a free, web-based BI tool that enables users to create interactive and customizable dashboards and reports, integrating seamlessly with other Google services. Domo, a cloud-based BI platform that integrates multiple data sources, offering real-time data analysis and predictive analytics capabilities. IBM Cognos Analytics, an AI-fueled BI platform that supports the entire analytics cycle, from discovery to operationalization, providing users with actionable insights and data visualization capabilities. Superscript 1 Superscript 2. Choosing the right BI tool. When selecting a BI tool, consider factors such as data sources. Ensure the tool supports your data sources and formats. Ease of use. Choose a tool with an intuitive interface and minimal learning curve. Scalability. Select a tool that can grow with your organization's needs. Integration. Consider tools that integrate well with your existing software stack. Cost. Evaluate the total cost of ownership, including licensing, implementation, and maintenance costs. Superscript 1. OLAP, that is online analytical processing. Online analytical processing is a category of data processing that enables users to easily and quickly analyze data from multiple perspectives or dimensions. It is primarily used in business intelligence, reporting, and decision support systems. Key features of OLAP. Multidimensional analysis. OLAP allows data to be modeled and viewed in multiple dimensions, e.g., time, geography, product. This enables users to slice, dice, drill down, roll up, and pivot data efficiently. Fast query performance. Designed for complex analytical queries that involve aggregations, OLAP systems pre-compute and store data in optimized structures like data cubes. Data aggregation. OLAP systems can summarize large amounts of data to produce reports such as sales trends, budget comparisons, or performance dashboards. Historical data analysis. OLAP supports analysis over historical data, helping organizations discover trends and patterns over time. Types of OLAP systems. MOLAP, multidimensional OLAP. Data is stored in multidimensional cubes. It offers fast query performance and efficient storage but may have limitations with very large datasets. ROLAP, relational OLAP. Data is stored in relational databases, and queries are generated in real time. It scales well with large datasets but may be slower for complex queries. HOLAP, hybrid OLAP. Combines features of MOLAP and ROLAP by storing some data in cubes and some in relational databases to balance performance and scalability. Applications of OLAP. Business reporting, e.g., sales, finance, marketing. Budgeting and forecasting. Customer relationship management, CRM. Supply chain management. Case study, OLAP implementation in a retail chain. Company, Megamart Superstores. Industry, retail. Objective, improve decision-making for inventory management, sales analysis, and regional performance. Problem statement. Megamart, operating 150 retail outlets across the country, faced challenges in analyzing sales trends across different regions and time periods, managing inventory based on customer demand patterns, generating reports for management with real-time insights. Solution, OLAP system implementation. Megamart deployed an MOLAP-based business intelligence, BI, solution using Microsoft SQL Server Analysis Services, SSAS. Key OLAP features utilized. Multidimensional cubes to analyze sales by product, region, and time. Drill-down capability to view sales performance from yearly to daily levels. Slice and dice to examine regional variations in customer preferences. Pivoting to dynamically compare product performance across stores. Results achieved. 30% faster report generation across departments. Improved stock control by aligning inventory with real-time sales trends. Enhanced marketing decisions through customer behavior analytics. Regional managers could view store-level KPIs instantly. Conclusion. the OLAP implementation optimizing operations and increasing profitability. Dashboards and reports. Dashboards. A dashboard is a real-time, interactive interface that visually displays important metrics, trends, and key performance indicators, KPIs. Dashboards are designed to monitor business activities and performance at a glance, enabling fast and informed decision-making. Key features. Real-time data integration connects with multiple data sources to show live data streams. Visual components. bar/line/pie charts. Scorecards. Geographic maps. Trend lines and filters. Customizable views. Users can personalize dashboards to show relevant data only. Interactive elements allow drill down, drill through, or filtering by parameters, e.g., by region, time, or product. Mobile-friendly, often designed to work on mobile devices for on-the-go access. Purpose. Provide quick insights. Monitor KPIs and operational metrics. Enable action based on up-to-date data. Types of dashboards. Operational dashboards. Focus on day-to-day operations, helping organizations track performance in real time. Strategic dashboards provide long-term data trends and outcomes, helping executives track overarching organizational goals. Analytical dashboards, used for deep data analysis, often contain complex visualizations and are characteristic of data exploration. Brain examples. Executive dashboard, company-wide KPIs like revenue, expenses, and customer churn. Sales dashboard, sales per region, targets versus actuals, top products. Operations dashboard, supply chain performance, production metrics. Integration in business intelligence, BI. Dashboards are often the first level of analysis, showing the what. Reports serve the second level, explaining the why with detailed data. Reports. Definition. A report is a detailed, structured document that presents data and findings in a formalized way, typically focusing on specific metrics or analyses over a set period. Unlike dashboards, reports are often static and may not update in real time. Characteristics. Historical data. Reports usually compile historical data, offering insights into trends over time, past performance, and outcomes. Structured format. They can include graphs, tables, and written analysis, providing a comprehensive assessment laid out in a logical format. Analysis and insights. Reports often provide summaries, conclusions, and recommendations based on the data presented, making them valuable for strategic planning. Regular intervals. Reports may be generated on regular schedules, e.g., weekly, monthly, quarterly, or as needed, offering comprehensive views based on specific timeframes. Conclusion. Both dashboards and reports serve critical functions within organizations, providing valuable insights that drive decision-making. Dashboards are best suited for real-time monitoring and operational awareness, while reports offer detailed analysis to support strategic planning and long-term goals. By effectively using both, organizations can leverage their data to enhance performance. Cloud-based business intelligence, BI. Cloud-based business intelligence solutions leverage cloud computing technology to provide businesses with tools and services that facilitate data analysis, reporting, and visualization. Here are some key features, benefits, and characteristics of cloud-based BI solutions. Description. Data accessibility and storage. Cloud-based BI solutions allow organizations to store their data on remote servers instead of on-premises infrastructure. This ensures that data is accessible from anywhere with an internet connection. Scalability. Businesses can easily scale their BI capabilities up or down based on their needs. This flexibility is beneficial for companies experiencing growth or varying workloads. Cost-effectiveness. Typically, cloud-based BI solutions operate on a subscription model, which can reduce initial capital expenditures associated with hardware and software. Pay-as-you-go pricing can also minimize costs during off-peak times. Real-time data analysis. Many cloud-based BI tools provide real-time analytics, enabling businesses to make timely decisions based on current data, enhancing agility and responsiveness. Collaboration features. Cloud platforms facilitate easy sharing and collaboration among users. Multiple stakeholders can work on reports and dashboards simultaneously, enhancing teamwork across departments. Integration capabilities. These solutions often integrate with various data sources, including databases, enterprise applications, and third-party APIs, making it easier to aggregate and analyze data from multiple platforms. User-friendly interfaces. Most cloud-based BI tools offer intuitive and graphical user interfaces, allowing users with varying levels of technical expertise to create reports, dashboards, and visualizations without needing in-depth programming knowledge. Security and compliance. Cloud providers typically implement robust security measures, including data encryption, access controls, and compliance with industry standards and regulations, e.g., GDPR, HIPAA. Automatic updates and maintenance. Software updates, maintenance, and security patches are handled by the service provider, ensuring that users always have access to the latest features and improvements without downtime. Advanced analytics and AI integration. Many cloud-based BI solutions incorporate advanced analytics capabilities, including predictive analytics and machine learning, enabling organizations to derive deeper insights from their data. Examples of cloud-based BI solutions. Tableau Online, a cloud version of Tableau that allows users to share and collaborate on dashboards and reports online. Power BI, Microsoft's cloud-based analytics service that enables data visualization and sharing insights across the organization. Google Data Studio, a free tool that turns data into informative, easy-to-read, easy-to-share, and fully customizable dashboards and reports. Data visualization. Principles of effective data visualization. Effective data visualization bridges the gap between raw data and actionable insight. It not only illustrates trends, comparisons, and relationships but also tells a compelling story that can guide decision-making. The following principles are foundational for creating meaningful, clear, and user-centered visual representations of data. 1. Clarity. Communicate without confusion. Clarity ensures that the visualization communicates the intended message directly and unambiguously. The design should eliminate noise, elements that do not add value or relevance to the message. Every visual component, title, axis, labels, etc., should serve a clear communicative purpose. Example: a cluttered pie chart with too many slices becomes unreadable, whereas a clean bar chart may deliver the same data more effectively. 2. Accuracy. Faithful representation of data. Accurate visuals represent data truthfully without manipulation or bias. This means using zero-based axes when required, especially in bar charts. Avoiding 3D effects that distort perception. Representing proportional relationships properly, e.g., area in bubble charts. Misleading charts may damage credibility and lead to poor decisions. 3. Appropriate chart selection, match form to function. Each type of chart is suited to a specific kind of data story. Bar charts for comparisons across categories. Line charts for showing trends over time. Pie charts for parts of a whole analysis. Heat maps for density or intensity representation. Scatter plots for correlation or distribution analysis. Choosing the wrong chart can obscure the insight instead of illuminating it. 4. Color usage. Purposeful and accessible color should help differentiate groups or highlight anomalies. Represent intensity or order, e.g., light to dark for low to high. Respect accessibility, e.g., red-green color blindness. Using too many or irrelevant colors can confuse the viewer. Contrast should be used to draw attention, while similar values should use consistent hues. 5. Focus and emphasis. Guide the viewer's eye. Good visualizations help the viewer focus on the most important data. This can be achieved by using bold fonts, bright colors, or larger markers for emphasis. Isolating key points with annotations or callouts. Ordering data, ascending or descending, to enhance comparison. This principle supports storytelling by highlighting what matters most. 6. Contextualization, data in the right frame. Numbers mean little without context. Effective visualizations provide reference points like time comparisons, e.g., year-over-year growth, industry benchmarks, historical trends or forecasts. Without context, viewers may misinterpret the significance or normalcy of a data point. Storytelling with data. Storytelling with data is the practice of conveying insights from data using a narrative structure that resonates with the audience. Instead of simply presenting numbers or charts, it transforms analytical results into meaningful stories that drive understanding, engagement, and action. Here's a detailed breakdown of its core elements and importance. 1. Purpose-driven narrative. Before visualizing the data, it's essential to clarify the why. What message are you trying to convey? What action do you want the audience to take? How does the data support your point? A story gives direction to data by turning insights into persuasive, relatable, and memorable content. 2. Audience awareness. Tailor the story based on audience knowledge, technical versus non-technical, their interests and roles, the level of detail they need. For instance, a CFO might want financial trends, while a product manager cares about user behavior metrics. 3. Structured framework. Effective data storytelling often follows a familiar narrative arc. Beginning, set the context. Introduce the problem or question. Middle, present the data and insights that address the issue. End, conclude with actionable takeaways or decisions. This structure makes the information more digestible and purposeful. 4. Relevant data selection. Avoid overwhelming the audience with all available data. Instead, select data that directly supports the narrative. Filter noise and highlight what's significant. Emphasize trends, comparisons, or anomalies that tell the story best. 5. Effective visualizations. Visual elements should complement the story, not distract. Use appropriate charts, e.g., bar, line, heat maps, for the data type. Highlight key points with colors or annotations. Keep the design clean and focused on the message. 6. Emotional engagement. Good data stories connect emotionally. Use relatable scenarios or analogies. Humanize the data, e.g., instead of 20% increase in churn, say 1 in 5 users left the service. This helps the audience internalize the message and feel its impact. 7. Call to action. A powerful story leads to a clear conclusion. What should be done next? Is a decision needed? What is the business implication? The story must translate into a business impact or insight. 8. Consistency and credibility. Ensure all visuals, metrics, and data sources are consistent and accurate. Avoid cherry-picking or misleading representations. Maintain trust by explaining data sources and methods when needed. 9. Iterative improvement. Data stories benefit from iteration. Gather feedback from test audiences. Refine the visuals or the narrative based on clarity and impact. Use versioning to track story evolution for different stakeholder needs. Building dashboards and KPIs. Creating effective dashboards and key performance indicators, KPIs, is central to data-driven decision-making in any organization. This process involves combining data visualization, business intelligence, BI, and performance measurement methodologies to provide clear, actionable insights. 1. Understanding the purpose. Dashboards. A dashboard is a visual interface that consolidates and displays critical data points and metrics in a clear, interactive, and real-time format. It allows users to monitor the health of an organization, department, or project at a glance. Types of dashboards. Strategic dashboards, focused on high-level KPIs for executives. Operational dashboards, monitor day-to-day processes and performance. Analytical dashboards, provide deeper data exploration and insights. KPIs, key performance indicators. KPIs are quantifiable measurements used to evaluate the success of an individual, team, or organization in meeting objectives. Good KPIs should be smart, specific, measurable, achievable, relevant, and time-bound. 2. Steps to building effective dashboards with KPIs. Step 1. Define objectives. Identify business goals and decision-making needs. Determine the target audience, e.g., executives versus analysts. Align KPIs with strategic objectives. Step 2. Identify and define KPIs. Choose KPIs that reflect performance success, e.g., revenue growth rate, customer retention, net promoter score. Use both leading indicators, predict future trends, and lagging indicators, reflect past performance. Define the calculation method, data source, and update frequency. Step 3. Data collection and integration. Aggregate data from multiple sources, databases, CRMs, ERPs, spreadsheets, APIs. Ensure data quality, remove duplicates, handle missing data, and normalize. Step 4. Select visualization tools. Common tools: Power BI, Tableau, Google Data Studio, Looker, ClickSense. Visualization elements: charts, line, bar, pie, donut. Gauges, scorecards, heat maps, filters and slicers for interactivity. Step 5. Design the dashboard. Start with a wireframe or mock-up. Ensure a logical layout, e.g., top-down, strategic to operational. Use consistent color schemes and labeling. Ensure responsiveness, works on desktop and mobile. Limit to 5 to 7 KPIs per screen for clarity. Step 6. Implement and test. Load real-time or batch data into the dashboard. Validate metrics and ensure accuracy. Test with real users to gather feedback. Step 7. Deploy and maintain. Share with stakeholders via cloud, app, or embedded reports. Schedule data refreshes. Set alerts for threshold breaches, e.g., drop in performance. Review and refine periodically. 3. Best practices. Contextualization, include trends, targets, and comparisons, e.g., versus last month or year. Interactivity, allow filtering, drill down, and export options. Storytelling, use annotations and data highlights to explain key insights. Accessibility. Ensure usability for non-technical you. Data mining and machine learning in business intelligence, BI. Introduction to data mining and machine learning in business intelligence. In the rapidly evolving world of data-driven decision-making, business intelligence, BI, has emerged as a crucial framework for organizations aiming to gain strategic insights and stay competitive. Central to modern BI are data mining and machine learning, two powerful technologies that enable the extraction of actionable patterns and the prediction of future trends from vast datasets. Data mining refers to the process of discovering hidden patterns, relationships, and anomalies within large datasets. It utilizes techniques from statistics, database systems, and artificial intelligence to transform raw data into meaningful information. This process involves steps such as data cleaning, integration, selection, transformation, pattern discovery, and knowledge presentation. Common applications include market segmentation, customer churn prediction, sales forecasting, and fraud detection. Machine learning, ML, a subset of artificial intelligence, enables systems to automatically learn and improve from experience without being explicitly programmed. When applied within BI, machine learning models analyze historical and real-time data to predict outcomes, classify behaviors, and recommend optimal actions. ML algorithms, such as decision trees, neural networks, support vector machines, and ensemble methods, can be trained on business data to detect customer preferences, personalize recommendations, optimize supply chains, and more. By integrating data mining and machine learning, BI systems can evolve from merely reporting and visualizing data to providing predictive and prescriptive analytics. This shift empowers decision-makers to not only understand what has happened in the business but also to anticipate what is likely to occur and what actions should be taken. Ultimately, the synergy between data mining, machine learning, and BI allows organizations to transform data into intelligence and intelligence into action, fueling innovation, operational efficiency, and strategic advantage. Applications in BI: predictive analytics, forecasting sales, customer churn, and market trends. Customer segmentation, identifying high-value customers and personalizing marketing efforts. Anomaly detection, identifying unusual patterns or outliers in data. Recommendation systems, suggesting products or services based on customer behavior. Benefits: data-driven decision-making, accurate insights inform business strategies. Improved efficiency, automated analysis and prediction reduce manual effort. Enhanced customer experience, personalized recommendations and targeted marketing. Forecasting, clustering, and classification in data mining and machine learning. Forecasting, clustering, and classification in data mining and machine learning. In business intelligence and advanced analytics, forecasting, clustering, and classification are three core techniques used to derive insights from data and drive informed decision-making. Forecasting. Forecasting involves predicting future values or trends based on historical data. It uses time series analysis, regression models, and machine learning algorithms to estimate future demand, sales, inventory needs, or market trends. Accurate forecasting helps businesses plan resources, manage risks, and make proactive decisions. Common tools include ARIMA models, exponential smoothing, and recurrent neural networks, RNNs. Applications of forecasting include predicting sales and revenue, estimating demand for products or services, identifying seasonal trends and patterns. Clustering. Clustering is an unsupervised learning technique used to group similar data points based on patterns or characteristics. It does not rely on predefined labels. Clustering helps identify hidden structures in data such as customer segments, purchasing behaviors, or anomaly detection. Popular algorithms include k-means, discan, and hierarchical clustering. This technique is widely used in marketing, fraud detection, and customer relationship management. Applications of clustering include customer segmentation, identifying high-value customers or customer groups. Market segmentation, identifying target markets and tailoring marketing efforts. Identifying patterns in customer behavior. Classification. Classification is a supervised learning method used to assign data into predefined categories or classes. The algorithm learns from labeled training data and applies this knowledge to classify new, unseen instances. Examples include email spam detection, loan approval, disease diagnosis, and sentiment analysis. Common classification algorithms include decision trees, random forest, naive Bayes, and support vector machines, SVM. Applications of classification include spam filtering, classifying emails as spam or non-spam. Product recommendation systems, recommending products based on customer behavior. Credit risk assessment, predicting the likelihood of loan default. Prescriptive analytics for decision support. Prescriptive analytics is the final frontier in the evolution of data analytics, offering the capability to not only predict outcomes but to also advise on possible decisions and recommend specific actions to achieve desired results. As an essential pillar in the decision intelligence ecosystem, it combines insights from descriptive and predictive analytics and applies them within a decision-making framework to answer the question, what should we do next? Key components. Prescriptive analytics uses a combination of optimization algorithms, mathematical techniques, e.g., linear programming, mixed integer programming, that determine the most efficient allocation of resources or optimal decision paths. Simulation modeling, testing different scenarios to understand the implications of various strategies before implementation. Heuristic methods, rule-based logic and expert systems for making decisions in complex or uncertain environments. Reinforcement learning, advanced machine learning that learns optimal actions through trial and error, commonly applied in dynamic decision-making environments. How it supports decision-making. Prescriptive analytics systems often operate in real time, helping organizations evaluate multiple future scenarios using predictive models. Identify constraints, e.g., budgets, capacities, legal regulations. Generate actionable recommendations aligned with business objectives. Continuously learn and refine decision policies based on outcomes and new data. This makes it invaluable in dynamic sectors such as healthcare, recommending individualized treatment pathways that balance efficacy, cost, and patient risk. Retail, suggesting optimal pricing strategies or inventory management decisions. Logistics, determining the best transportation routes and warehouse operations. Banking, proposing credit offers, risk mitigation tactics, or fraud responses. Energy, managing power grid loads, renewable integration, or predictive maintenance schedules. Technological enablers. Prescriptive analytics is powered by big data platforms, e.g., Hadoop, Spark. Cloud computing for scalable processing. AI or ML engines for adaptive modeling. Business rule management systems, BRMS, for codifying policies. Decision automation tools that close the loop from insight to action. Benefits. Increases operational efficiency. Reduces uncertainty and decision-making time. Improves resource utilization. Enhances customer satisfaction through tailored strategies. Supports evidence-based, strategic decision-making. By leveraging prescriptive analytics, organizations can make data-driven decisions, optimize operations, and drive business growth. Business intelligence, BI, applications in finance, marketing, supply chain, and healthcare. BI applications in finance, marketing, supply chain, and healthcare. 1. Finance. Business intelligence tools transform financial data into meaningful insights, helping organizations improve profitability, manage risk, and ensure compliance. Risk management, detect fraud patterns, assess credit risks, and monitor real-time financial health. Performance analytics, analyze profitability, return on investment, ROI, and cost efficiency across business units. Forecasting, predict cash flow, revenue trends, and investment performance using time series analysis. Regulatory compliance, automate financial reporting and ensure adherence to financial laws and standards. 2. Marketing. BI empowers marketers to make data-driven decisions that enhance customer engagement and campaign effectiveness. Customer segmentation, identify target audiences using clustering techniques and behavioral data. Campaign analysis, track campaign ROI, conversion rates, and customer acquisition costs. Sentiment analysis, use natural language processing, NLP, on social media and reviews to gauge brand perception. Personalization, create dynamic marketing strategies based on customer behavior and preferences. 3. Supply chain management. BI provides real-time insights that drive supply chain efficiency and responsiveness. Inventory optimization, monitor stock levels, reduce excess inventory, and prevent stockouts using predictive analytics. Supplier performance, evaluate vendor reliability, lead times, and cost metrics. Logistics and transportation, optimize routes, reduce delivery times, and minimize shipping costs through prescriptive models. Demand forecasting, use historical sales data to anticipate future demand and plan procurement accordingly. 4. Healthcare. In healthcare, BI enhances patient care, operational efficiency, and policy making. Patient analytics. Analyze patient demographics, medical history, and treatment outcomes for personalized care. Clinical decision support, provide doctors with evidence-based treatment recommendations. Operational analytics, improve resource allocation, reduce wait times, and manage hospital workflows. Public health surveillance, monitor disease outbreaks, vaccination progress, and community health trends. Ethical and legal considerations in business intelligence. As organizations increasingly rely on business intelligence, BI, to guide strategic decisions, the ethical and legal frameworks surrounding data usage have become critical. While BI offers powerful insights, improper handling can lead to data misuse, discrimination, privacy violations, and legal consequences. Therefore, ethical governance and compliance are essential to ensure responsible BI practices. 1. Ethical considerations. A. Data privacy and consent. Individuals must have control over how their data is collected, stored, and used. BI systems should follow informed consent principles when dealing with personal or sensitive information. Anonymization and pseudonymization are recommended to protect identities. B. Transparency and explainability. BI models and insights must be understandable and interpretable to stakeholders. Avoid black box decision-making, especially in sensitive applications like credit scoring, hiring, or healthcare. C. Bias and fairness. Datasets may reflect historical or societal biases, leading to unfair decisions. BI practitioners must identify and mitigate algorithmic bias in model design and data selection. D. Accountability. Clear accountability must be established for data errors, misuse, or harmful outcomes derived from BI systems. Ethical responsibility lies not only with data scientists but also with decision-makers who act on insights. E. Purpose limitation. Data should be used strictly for the purpose it was collected. Secondary use without consent or alignment with ethical norms is discouraged. 2. Legal considerations. A. Data protection regulations. GDPR, EU ensures users' rights to access, rectify, and erase their data. CCPA, California, and other regional laws govern data access, disclosure, and opt-out provisions. BI platforms must be compliant with these laws to avoid severe penalties. B. Intellectual property and data ownership. Clarify who owns the data, insights, and BI reports. Unauthorized use of third-party data or algorithms can lead to infringement claims. C. Industry-specific regulations. Healthcare, HIPAA compliance for health-related data. Finance, SEC and FINRA guidelines on audit trails, data retention, and fair practices. BI systems must align with such domain-specific legal standards. D. Data security laws. BI solutions must implement robust encryption, access controls, and audit mechanisms to prevent data breaches. Compliance with cybersecurity frameworks, e.g., ISO/IEC 27001, NIST, is often mandatory. E. Anti-discrimination laws. Insights or decisions that result in biased treatment based on race, gender, or age may violate civil rights laws. Ethical audits and fairness checks are essential. Conclusion. Ethical and legal considerations in BI are not optional. They are foundational to trust, sustainability, and compliance. Real-world case studies in business intelligence, BI. Business intelligence isn't just theory, it's being actively used across industries to transform data into strategic decisions. Below are select real-world case studies that demonstrate how leading organizations use BI tools and analytics to drive performance, efficiency, and innovation. 1. Walmart, inventory optimization. Challenge, managing millions of SKUs across thousands of stores globally. BI solution, implemented a real-time BI system for tracking inventory levels, customer purchasing behavior, and supply chain performance. Impact, reduced overstocking and stockouts, improved demand forecasting, and optimized shelf space utilization. 2. Netflix, personalized recommendations. Challenge, retain users and improve content engagement. BI solution, leveraged machine learning and BI tools to analyze viewing habits, ratings, and search behavior. Impact. Personalized user experience led to increased watch time and subscriber retention, contributing to their market leadership. 3. Amazon, dynamic pricing and customer insights. Challenge, staying competitive in a highly dynamic e-commerce environment. BI solution, used BI and predictive analytics for pricing strategies, customer segmentation, and targeted promotions. Impact, improved customer satisfaction, conversion rates, and profit margins. 4. Mayo Clinic, clinical decision support. Challenge: improving patient outcomes while managing large volumes of clinical data. BI solution: integrated BI with EHR, electronic health record, systems to support data-driven medical decisions. Impact: enhanced diagnosis accuracy, better resource allocation, and improved patient care quality. 5. Starbucks, location and product insights. Challenge: selecting new store locations and managing local customer preferences. BI solution: used geospatial BI and customer behavior analysis to optimize site selection and menu design. Impact: higher profitability per store, better customer engagement, and more successful product launches. 6. DHL, logistics optimization. Challenge: managing global logistics operations and delivery routes. BI solution: implemented BI dashboards for tracking shipments, route planning, and delivery performance. Impact: reduced fuel costs, faster deliveries, and higher customer satisfaction. Business intelligence, BI, maturity models. A BI maturity model provides a structured framework to evaluate how effectively an organization uses data and analytics. It outlines the evolution from basic data reporting to fully integrated, predictive, and strategic decision-making. These models help organizations assess current capabilities, identify gaps, and strategize future BI investments. 1. Common BI maturity model stages. Stage 1, Data awareness. Characteristics: data exists but is fragmented and unstructured. BI tools: none or limited to spreadsheets. Decisions: based on intuition, not data. Challenges: low trust in data, manual processing, data silos. Stage 2, Data management. Characteristics: data is centralized and governed with basic data quality controls. BI tools: basic dashboards and reporting tools. Decisions: based on historical reports. Focus: operational monitoring, basic insights. Stage 3, Business intelligence. Characteristics: organization uses descriptive analytics across departments. BI tools: interactive dashboards, ETL tools, SQL-based analysis. Decisions: informed by data, some automation. Benefits: improved efficiency, shared data culture. Stage 4, Advanced analytics. Characteristics: use of predictive and prescriptive analytics, machine learning models. BI tools: predictive modeling tools, AI-based recommendations. Decisions: proactive and forward-looking. Benefits: scenario planning, trend forecasting, better ROI. Stage 5, Data-driven culture. Characteristics: data is embedded in all business processes and strategic decisions. BI tools: real-time analytics, cognitive systems, self-service BI. Decisions: automated, optimized, and contextual. Benefits: competitive advantage, innovation, organizational agility. 2. Popular BI maturity frameworks. Gartner's maturity model focuses on data quality, analytics capability, governance, and cultural adoption. TDWI maturity model covers 5 levels: nascent, opportunistic, repeatable, managed, and optimized. Deloitte or IBM models often emphasize governance, architecture, and innovation readiness. 3. Use of BI maturity models. Self-assessment: identify the current state of BI in your organization. Strategic planning: determine BI priorities and roadmap. Benchmarking: compare against industry standards or competitors. Resource allocation: prioritize investments in people, tools, and processes. ROI and performance metrics in business intelligence. 1. ROI, return on investment, in BI. ROI measures the financial return an organization gains from its investment in BI tools, technologies, and processes. Calculating ROI ensures that BI initiatives are aligned with strategic goals and contribute tangible value. Sources of ROI in BI. Cost reduction, improved operational efficiency and automation. Revenue growth, better market targeting and customer segmentation. Risk mitigation, enhanced forecasting and fraud detection. Time savings, faster decision-making with real-time data access. 2. Performance metrics in BI. Performance metrics help evaluate how effectively BI tools and strategies are meeting business objectives. These metrics fall under different categories. A. Operational metrics. Query response time. Report generation time. Dashboard load speed. ETL throughput. B. Business impact metrics. Decision-making speed. Process improvement rates. Customer retention rate. Sales growth attributed to BI insights. C. Adoption metrics. User adoption rate. Frequency of BI tool usage. Number of self-service reports created. D. Data quality metrics. Data accuracy rate. Data timeliness. Duplication/error rate. 3. BI KPIs, key performance indicators. By Roy. Cost per report or insight. Number of automated processes. Revenue influenced by BI analytics. Data to decision cycle time. Change management and adoption challenges in BI. Implementing business intelligence systems involves more than just technology, it requires a shift in organizational culture, processes, and behavior. Change management is critical to ensure that BI tools are effectively adopted and integrated across the business. 1. What is change management in BI? Change management in BI refers to structured strategies and processes used to help individuals, teams, and organizations transition from legacy systems or manual reporting to modern BI platforms. It focuses on reducing resistance, increasing user acceptance, and sustaining long-term BI usage. 2. Common adoption challenges. Resistance to change. Employees may be skeptical or fearful about new systems due to lack of understanding or fear of job displacement. Lack of executive support. Without top-level buy-in, BI initiatives often lack direction and urgency. Inadequate training. Users may struggle to utilize BI tools effectively without proper training or onboarding. Poor data quality. If users don't trust the data, adoption suffers, even if the system is technically sound. Complex interfaces. BI tools with complicated dashboards or workflows can discourage usage. Siloed departments. Lack of cross-departmental collaboration can hinder data sharing and unified BI adoption. 3. Change management strategies. Leadership sponsorship. Engage leaders to promote BI as a strategic asset. User-centric design. Involve end users in BI development for better alignment with daily tasks. Training and support. Offer hands-on training, user manuals, and ongoing help desks. Communication plan. Keep all stakeholders informed about the benefits, timelines, and support available. Feedback mechanisms. Create feedback loops to refine BI tools based on user input. Gradual rollouts. Implement BI systems in phases to reduce overwhelm and ensure stability. 4. Key metrics to monitor adoption. User login frequency. Number of reports generated per user. Time to insight improvement. User satisfaction surveys. Percentage of decisions based on BI data.